problem we have, which I think you share, which is radio frequency interference, and some of the work we're doing on that. And then a little bit on commercialization. It sounds like we have something in common there as well. We have commercialization activities as well. And then I'll finish up talking about how we go about training the next generation of engineers and scientists. So first of all, just a little bit about NRAO. The National Radio Astronomy Observatory is a federally funded research and development center, which means it is supported by the National Science Foundation on a 5-year contract, and the operation of the observatory is executed by a nonprofit company, in our case, Associated Universities, Inc., and we have a cooperative agreement with NSF for the funding, and then under the solicitation for the National Radio Astronomy Observatory, we're given the responsibility for running the observatory. Which includes operating a very large array in New Mexico. You see there, as well as the Green Bank telescope, the ALMA telescope in Chile that we manage with our 3 international partners, and the very long baseline array. And you see those here and what their frequencies are. One of the major initiatives at NRAO is to upgrade the Very Large Array into what we call the next generation VLA telescope, and I'll talk a lot about that, but you can see there that's going to involve a major expansion and increase in the capabilities of the VLA. Now let me go back just one slide here to talk about the Central Development Lab. This is it you see here in the very best drone shot we've ever had of the lab, so I use that shot a lot, but we're also in Charlottesville. We're in our 3,000 square feet of lab space at the laboratory, which includes plenty of electronics and radio frequency labs, as well as a chemistry lab where we do plating and electroforming. There are about 52 personnel working at CDL these days. That consists of research engineers who are responsible for charting a path for research and development for instruments of the future, and then test and evaluation and construction engineers, software engineers, technical specialists, machinists, and of course administration, which everyone needs. CDL differs from the other labs at the observatory is that we're not required to support directly the operation of any telescope, with the exception of ALMA. But we are responsible for developing the future instrumentation for that. Now, because we've developed a lot of instruments for telescopes, we do repair and participate in sustaining operations, but we don't have any day-to-day responsibilities for operating telescopes. Our mission is to think about the future in 5 years or 10 years down the road. So one of the biggest projects going on now is an upgrade to ALMA, particularly the Band 6 ALMA, which is 200 to 300 gigahertz. I'll talk about that in a second. But the general idea behind ALMA is to increase the bandwidth at least by a factor of 2, and eventually by a factor of 4, while increasing the sensitivity, which is a tall order, but we're making progress. And you see here some of the current bands in ALMA and how we want to expand both the RF and the IF frequencies. As far as Band 6, which is the one we're currently working on upgrading, it currently operates from 211 to 275 gigahertz. And you'll see we're looking for a modest increase in RF frequency down to about 208 gigahertz or so, and up to about 282. And you see with the increased IF bandwidth, we're going to be able to pick up a lot of these isotopologs for spectrum astronomy in the future, which is going to make operation of Band 6 more efficient. Here is a diagram of Band 6, just showing the parts that we've left in place and the parts that we've upgraded. I'm not sure if you're familiar with the ALMA receivers, but they are in a Dewar with 110 and a 15 and then a 15K section. There's a vacuum window and optical filter on the outside, and 2 infrared filters at 110K and 15K stages. We've left those in place, as well as the main two mirrors for directing energy into the feed horn. Everything in white you see here we've redesigned, which includes a new feed horn and an OMT, which coupled together better than on the original Band 6. There was a square to circular waveguide transition that we had to deal with, and we've taken care of that. New RF hybrids, and working with our partners at the University of Virginia, a new superconducting, insulating superconducting mixer we'll talk about a little bit, which is at the heart of a Band 6 receiver. We've also partnered with the Center for Astrophysics in building some isolators between the mixer and the amplifier to stabilize the system. We have built all new intermediate frequency amplifiers I'll talk about in a minute to increase the bandwidth. And we're partnering with Yevi's Observatory, who have built our RF hybrid. This part here is the warm cartridge, which is responsible for supplying a tunable LO. We've left most of that in place. The one exception, in order to get up to the 200 gigahertz LO, we previously were starting with a YIG oscillator and multiplying by 2 and multiplying by 3. We've changed out the YIG oscillator to be twice the original frequency, so we've eliminated the doubler and gone right to a tripler, and that has helped the amplitude noise on the LO, which is helping us meet our sensitivity requirements. Okay, here's what the cartridge looks like, but first I want to talk about the mixer and the performance. So we were required to meet a minimum of 4 to 16 gigahertz intermediate frequency with the goal to go to 4 to 20. And we wanted to extend the RF frequency range as you see here. I'll show a slide in a minute that shows that the current Band 6 IF region is not as flat as it could be. So we wanted to flatten out the IF response, and we of course wanted to increase it. And we also wanted to improve the optics to help the polarization separation, as well as a side lobe problem we had on the antenna. So at the heart of the Band 6 receiver is a SIS mixer that's made by our partners at the University of Virginia. These are designed at NRAO, and then we work with the fabrication facility at the university to produce these. There's a couple of things we had to do to meet the goals of the wideband sensitivity upgrade. First of all, in order to increase the RF bandwidth and the IF response, you had to build a smaller junction with less parasitics. So that required increasing the critical current density on a superconducting junction like that. So that required redesigning the junction and making it small and making sure that the fabrication process held those tolerances. The other thing we had to do was to eliminate or minimize the leakage current, which is the quasi-particle flow that you get across the junction unintended, without a bias voltage on. And the way to control that is to make sure that the size and the thickness of that very small aluminum oxide layer, which is the insulator, is uniform. And the University of Virginia came up with a few techniques to do this. I don't know why this is... that is done by carefully and dynamically controlling the pressure and the rate of putting down that oxidation level. So they've developed a dynamic system to do that, and we're getting very good results. You'll see on the next slide. So we have been working on getting this mixer optimized to meet our specs for almost 4 years now, and you'll see that we just passed a preliminary design review and presented results, and we're getting very good results, and I think we finally have arrived at our final design. But the lesson there is, if you're improving a millimeter wave receiver, the majority of your work goes into the superconducting mixer. If you haven't seen it, here's what the inside of the cartridge looks like. Here's the feed horn. You go into an OMT, and then you have two separate polarization chains coming out, which go into a mixer, and then a IF amplifier. and onto the warm cartridge for second amplifier to equalize the IF response, and onto a digital section. The other project we had to work on was the IF amplifier. You may be familiar with the Cryo 3 amplifiers, which for some 20 years now or more have been the gold standard for amplifiers in radio astronomy. Those are exhausted now. There are not enough of those left to do projects. So we have partnered with the Swiss company Duramics, which is really building some of the fine cold or something that's keeping me from talking. Okay. One minute. Okay. I think I'm back. Okay, the next project is the next generation VLA I talked about. The idea here is to increase the sensitivity by a factor of 10 on the VLA. Excuse me. As well as increase the resolution by a factor of 10. So you see, in order to do this, we have to greatly increase the number of antennas from 27 to almost 150. And we have to increase the baselines from 20 kilometers to over 1,500 kilometers. It will consist of 3 basic sections. A core section, which more or less is at the location of the current VLA. So about 75% of these antennas will be inside the footprint of the current ngVLA. Then we'll have a mid-span, which will go out to about 500 kilometers. And then finally, we will integrate the current very long baseline array sites into this antenna, or into this telescope. And you can see the long baseline positions here. The timing and frequency distribution will be complicated for this. We think within the core, the 114 or so antennas that are within about a kilometer footprint, and the other spiral arms you saw, which are in about a 30 kilometer distance, we'll have no problem pushing out time and LOs on dedicated fiber optic for these. And depending on what kind of public infrastructure is available, we might be able to distribute that with existing public fiber optics. The ngVLA will need about 50 nanoseconds of time resolution between antennas, so that's possible. That is not possible with those 1,500 or 3,000 kilometer baselines. So those will rely on hydrogen maser, just like the VLB currently does. Okay, here you see kind of where the ngVLA will fit in as far as sensitivity of affected area versus T-cis versus frequency. You can see it will greatly below 50 gigahertz will improve the sensitivity and the spectral resolution of the current VLA. It will actually outperform some of the lower ALMA frequencies. So it is. It performs very well, especially in its mission. One of its missions is to look at how planets are formed. So, up to its highest frequency at about 150 gigahertz at 0.3 centimeters, it will perform very well as far as angular resolution goes. And then as you go down from that, it will also be a superb pulsar engine as well. Here's the way that will be laid out. Like I mentioned, the core, which is where most of the antennas are, will be within a few kilometers of each other, and then the spiral will go out to about 40 kilometers. And then you have the mid and the long here. And then for power measurement, there's a short baseline array. We will go from 1 gig to 115 gigahertz with 6 receivers you see there, and you see how those are laid out. There's a single cryostat package that sits on these arms here. And that will be on a translation stage, so we will just simply move these feed horns left and right in front of that subreflector you see there to change receivers. So that box looks like this. Band 1, the 1 to 2 approximately gets its own cryostat and receiver, and then bands 2 through 6 will be in a separate cryostat. And you see the LOs and other command monitoring control systems go there. And there's a cross view of how the front ends on all the antennas look similarly. So one of the major development efforts we have at the Central Development Lab is working on these receivers. And we're doing that under our integrated receiver program, where we've had the philosophy for a few years now to remake centimeter wave radio astronomy receivers. What we want to do is take advantage of all the digital technology improvements that have happened in the last 20 years or so. And we want to integrate into a single package that would be inside a single cryostat on one chassis, the RF front end that does the mixing and the down converting and the digitization, and then the serialization into the photonics. So you've got RF, digital, and photonics all in a single chassis, digitizing as early as possible. You're minimizing the distance between those 3 functions and keeping any residual phase noise low and locking it down after digitization as soon as possible. So the idea is we will have a cryogenic RF amplifier that you saw on the slide before, but then inside this single chassis, which you see about the same size here, we'll have, for each polarization, sideband separating mixer, and then IF amplification, immediately digitizing and serializing and going to a photonic transmitter that will go to an amplifier onto the correlator. I'll show that in a second. But you see the level of integration we're looking at. We're trying to keep all the electronics, especially the RF end, as tightly coupled as possible, using mimics as possible, minimizing the number of runs that we have so that the phase noise is as low as possible and the system is as stable as possible, so that calibration does not have to be done as often as in the past. We're also working on the correlator for this. So the idea here is you have a digital backend that will do the analog digitization and channelization, and then there'll be a fiber interface box that will go to a central processing unit where we will do it's a XF correlator. We'll do the correlation if need be, but using switch fabric. We could also switch those channels to do beamforming. We could do the cross correlation for interferometry, and there's also a mode either through a sub-beam or the instrument itself. We could look at a pulsar. So we're currently prototyping this in an FPGA or perhaps an RF sock, and we're considering perhaps casting this into an ASIC in order to keep long-term costs down. But we haven't quite decided what that breakpoint is. For a project like ngVLA, about half of the project costs are antenna costs. So it's imperative that early on you have an antenna design that you know works, and you know the price is stable, and you can be sure that you want to eliminate the risk for the antenna. So we've already contracted one 18-meter prototype antenna. It's at the BLA site now, and we are currently instrumenting it for tests that will occur this summer, where we will do holography and pointing and stabilization tests just to make sure it's meeting all the specifications. If this goes well, then we feel a lot more confident about the overall cost of the project, since about half the cost is going to be the antennas, and then we can start concentrating a little more on instrumentation. Okay. The other big project going on is what we call ngRADAR, which is the idea of putting a high power radar on the Green Bank telescope, which is a 100-meter fully steerable antenna. We started this project before Arecibo fell, which is terribly unfortunate, but we were glad that we were already working on this so that hopefully within a few years we can have a similar capability. So we're partnering with Raytheon on this project, and what we're concentrating on now is putting a 700 watt pilot transmitter on the Green Bank telescope, and just testing out what the science capabilities are for this. So the idea here is you would transmit from Green Bank telescope, which is in the eastern part of the United States. Eventually we would like 500 kilowatts into that radar. Now we're doing 700 watts, which I looked is about half the power on my microwave oven, so it's not a terribly powerful radar. That goes to the target. The return signal comes back bistatically, and we are receiving these signals on the VLBA, of the 10 VLBA antennas that are spread across the US. So we started our first observations in 2020. I got an email this morning on how our last test went on Saturday, but I haven't had a chance to read it. But most of our observing has been looking at the moon and seeing if we could test for asteroids as well. So the missions here are planetary science and lunar science, as well as what they call planetary defense. So if there's an asteroid that might have a possibility of crossing our orbit, we could use the radar to get a really good track on its trajectory, its composition, and its spin, and all the things you need to do to tighten up the estimation of its trajectory. When we go from this 700 watt prototype system to a half megawatt system, we're going to have to make some changes to the Green Bank telescope. We can't put the transmitter out on this arm. It would be too heavy for that, because it comes with associated cooling and power hardware, as you can imagine. So the idea now is to put the transmitter here, have a subreflector hanging out on the feed arm here, and transmit your 500 kilowatts here, illuminate the beam, and then the signal goes out. This is more than 100,000 pounds or so. So this has to stay low. So it's a bit of an engineering challenge. And we also want to integrate this with regular science observations, radio astronomy observations for the Green Bank telescope. So this subreflector is going to be able to be stored and then put out automatically without anyone being up on the boom arm there. The idea here is if a discovery is made by another instrument like Rubin, or something that's doing a quick search, within a few hours we could switch and start observing with the radar. So we're looking for a highly automated system. So of the studies we've done with the 700 watt transmitter, now this is a synthetic aperture mode here, so it's not interferometry. You're receiving with a single antenna, and your cross-range resolution is gained by the fact that as the Earth rotates, you have a coherent aperture. So you're basically synthesizing a very large antenna with a very high angular resolution. And then range resolution is obtained by bandwidth, and we're sweeping about 150 megahertz or so continuous on an FMCW transmission. So we're getting about 10 meter or so resolution with this, and it turns out to be the highest resolution images of the moon taken from the surface of the Earth. And so here you see a picture of Tycho crater, and in the PowerPoint version of this, you can actually see that you can take a picture as the moon rotates. You would see this image rotating. So we're now working on improving this algorithm. Motion compensation is a real problem. You've got the Earth moving, you've got separation between the Green Bank telescope and the receiver, and the moon isn't exactly being still either. So there's a high order correction in motion compensation that we have to do, which still is going to be a large part of the project. So we will be doing these prototype tests on Green Bank for a few more years, and we're hoping by the early 2030s we can have the system at least under construction and being built. Okay, I want to switch now to RFI, which 5 years ago we never thought about, and now it's all we think about because of car radar, because of Starlink and all the other things going on. So we have a couple of initiatives going on. One is the operational data sharing practice. We've started with the Starlink folks. So in this case, we have a dynamic database that we share with Starlink. We upload to that database the frequency and the time and the position in the sky that we're observing. They ingest that data into their control software, and as a Starlink satellite is coming over one of our sites, if there's a chance of getting in our beam, they will either change the frequency or move their steerable beam away from us. What we're going toward here is a dynamic radio quiet zone as opposed to a national radio quiet zone or a static quiet zone. So in the future, we don't think you can just map out a part of the ground where there can be no radio interference. That will just be impossible. But the idea is anyone coming into your zone who wants to share spectrum with you will have to see where you're observing and try to avoid you. And just because of the dynamics of the situation, that could just be 15 or 20 seconds or a minute. It's not overburdensome for them as long as they have the capability to avoid you. And here you see an example of how that works. Here's Green Bank Telescope making an observation. This curve here is kind of the baseline noise on the receiver, and without the operational data sharing, you can see there's increased noise throughout the IF bandwidth as the Starlink antennas come over. But once we implemented that, you can see that it's pretty much back to baseline level. So the CDL's responsibility in this is that we're currently building a series of spectrum monitors. Our first prototype is going from 1 to 50 gigahertz. It will scan the environment using 4 phases from horizon up to above 70 degrees elevation. It will identify flag signals. It's fully, it does full polarimetry up to 20 gigs, and it does direction finding as well. So one of our early prototypes there, you see, which looks a little bit like R2D2. We tested at Green Bank a couple of summers ago. This is a plot of frequency versus the difference in amplitude. Basically, if it's highly polarized, it shows up high here, and if it's a highly polarized signal, it's probably not. It's probably artificial and from some system. And we found a lot of stuff at Green Bank in our National Radio Quiet Zone that probably shouldn't have been there, but we were able to find these and geolocate them. It turns out there's someone right across the street from the observatory using a wireless phone, which is not necessarily allowed, but at least we know now, right? So we are just getting ready to finalize our full version of this. You can see it has 4 sides to it. We have a homemade sinuous antenna, which goes from 1 to 20 gigahertz. And then 3 other antennas that take us up to 50 gigahertz. We've got a switchable down conversion system going into a compact spectrum analyzer, which is doing all the heavy lifting signal processing work for us. And we're simply comparing amplitude versus frequency in order to get direction finding, which works amazingly well. The limits are, here are frequency. We eventually want to go up to 150 gigahertz, like the ngVLA would require. We're not as sensitive as a radio telescope. You can't be. These aren't cryogenic receivers, and our aperture isn't as large. But the idea is to use this either at a prospective site where we might want to put an ngVLA telescope, or at a current site to see if there's some problems with the correlator, or whether we have any evidence that it was caused by RFI interference. So this should be tested starting this summer, and then put in the field in the fall. Let's see. And lastly, I'm going to talk about commercialization a little bit. We have created a line of what we call reflections filters. It turns out that multipliers, mixers, and maybe A to D devices, you're going to get transients, which are going to cause standing waves in the system. If you have plenty of energy, like a radar system or a communication system, the small standing waves won't be a problem. They are a problem within radio astronomy, so we had an engineer design a unique system that basically takes those reflections and shoves them to ground inside the structure of the antenna. And we've partnered with many circuits, and we've had a reasonable commercial success of giving many circuits the license to produce these and share profits with them. And then, so these go up to about 20 gigahertz or so. We're working on a new line of transmission line versions of these, which will go up to at least 200 gigahertz. So we're shooting for 300 gigahertz. We're partnering with NRAO to do a thin film deposition version of that. So these will be used on the new ngVLA receivers as one of the ways to try to minimize the noise in those. The other thing we did commercially is, I don't know if you followed, a few years ago, the U.S. had a partnership with NASA where a couple of private companies were trying to put landers on the moon. This was the build cheap, fail early, crash often, but learn kind of philosophy. One of those companies was Intuitive Machines. And if you remember, their lander landed on the moon and then shortly thereafter flipped over. On their first flight, they were having some problems maintaining communications with their spacecraft. They had a downlink station in the eastern United States in Kentucky, and then they had one in Australia. And so it was hard to connect those two. And then they had one somewhere in Asia or Eastern Europe. But then they read about the VLBA, which runs all the way from Hawaii to the Caribbean, and that's a perfect connection between, the Western Hemisphere, and then when Australia starts to come up. So we agreed to partner with them to use the VLBA on their mission. It's a 1 week trip out to the moon. It lands on the moon, and it's there a week, and then it's done. So it's a 2 week mission. Since we only have to use one VLBA antenna at a time, it's not disruptive to our science mission. So we thought this was a perfect situation for us to try to use the VLBA for something commercial and something, fun, going to the moon. So we signed up with them to do this project. The only problem is the VLBA automatically digitizes at a bit depth of 2 bits, which is what the state of the art was in the 80s or the 90s when the VLBA was built. And it also puts this VDIF wrapper on it, which is the universal coding on data for long baseline astronomy. And the Intuitive Machine model was to provide the downlink partners with the analog 40 megahertz baseband receiver, because their model there was you would just hire someone with a dish, and they would, like a bit pipe, down convert the analog to 40 megahertz and send it on their machine. So we had the problem of having to convert, that 256 megabits per second at a bit depth of 2 with the VDIF format around it. We had to strip off that format. We had to upsample and then do a D to A at the right frequency to get to their box. So it wasn't trivial. But we did that with an FPGA and then a JESD D to A converter. And the lesson we learned there is we won't do that way. We will now use an RF socket in the future. But you see, the advantage here is you have all these 10 antennas. They all come into Socorro, so you can just switch antennas with the switch. And so if you just put one of these conversion boxes at Socorro, so this has the input of the VLBA data, it strips out the VDEF, it upsamples, and then it converts it down to a 40 megahertz signal. And it worked great. The IM mission, the second one, immediately fell over, unfortunately. But what we were able to do, they weren't able to get energy from their solar panels because it was oriented correctly, so they had just a couple of hours of energy left, power left on board. Their high gain antenna used for video and images was not pointed in the right direction, so they had to use a low gain antenna. But we basically switched to the VLA and phased the VLA up into a single antenna pattern and ran it through the system we built. And we're pretty sure this sad image of the lander on its side came through the VLA. And otherwise, we don't think they could have gotten that image. They are scheduled for another launch late this year, early next year, and we will be working with them as well. So that was a really good project for it. It was a short-term project. It was innovative. It did not disrupt our science operations, and we hope to do more of that in the future. That was the perfect mission for us. Okay, finally, I want to wrap up. I know one of your missions is to develop future engineers and astronomers, and we're the same. So we have postdocs at CDL. We have sabbatical engineers. Some of you may know Ricardo from the University of Chile, who recently spent a year with us. And then we have undergraduate and graduate students come and spend 6 months with us in the USA. Many engineering schools have a co-op program where the students come for 1 semester or about 6 months. And the idea here is that they would come spend 6 months with us, go back to school, and come spend another 6 months with us. And then if we happen to have an open position, they're ready to step right into it without any training. And we've done that once. Matthias here, who came from the Rochester Institute of Technology, joined us just as he graduated. We had an opening and it worked out perfect. So we have a pipeline of students coming in because it is, as you know, it is very hard to find electrical engineers and physicists and technical specialists to come into radio astronomy. Okay, I hope I didn't take too much time, but I'd be glad to answer any questions. And again, thank you for hosting me today. I enjoyed seeing your observatory.
When you showed the monitoring, the radio monitoring for looking for RFI, you showed the sinusoidal.
Sinuous?
Yes, that antenna. The shape of the instrument caught my attention. It's sort of hypnotizing. Would you explain it?
Yeah, so that is dual polarized. And so essentially you have half wavelengths. You can see it on the low frequency side. You have a half wavelength here. And then you have one at 90 degrees and one at 90 degrees and one at 90 degrees. So this is approximating a half wavelength. So the antenna is sensitive to that frequency. And then it repeats itself as it goes down in smaller and smaller components. So if those are uniformly built and the spacing is just right, and then on the back end, you have to carefully, take those. You have 4 outputs there. You have 2 polarizations and then the differential signal between those. Then you have to carefully convert those into an amplifier. So the magic is there. It's sinuous antennas are not new. They've been around a long time, but they are mesmerizing. I agree. If we could spin it, we could probably make you dizzy. Yeah, so we're actually very proud of that antenna because the design to get that much bandwidth. We look there's not there are not many antennas on the commercial market with that kind of bandwidth with a constant gain. It's not a high gain. It's a few dB, but it's very constant. So it's perfect for us because as you're trying to go from 1 to 50, it takes 40% of that bandwidth is done with just one antenna. So it's made it a little cheaper. Yes.
Thank you for the presentation. It's amazing all the work you do there, technology, and the results from the radar images of the moon.
Yeah, those are cool. Yeah, those are very cool.
And regarding this RFI with the Starlink satellites, and so I didn't know this, but do they have to comply with the rules of the Earth regarding like stopping their transmissions?
They do not have to comply. They are not. They're not violating any of the FCC spectrum regulations. So it's to their credit that they voluntarily agreed to collaborate with us. And we're very thankful for that. It shows a level of responsibility and spectral sensitivity, and they don't want to be seen as the ones that destroy passive science observations. So no.
And they know they don't have any client there, right? It's like...
That's true. They have the client of popular opinion, I think, right? And so I think they recognize that it helps everyone to do that. So I give them credit for all the things that companies could and can do. They're being extremely responsible.
But there are laws to protect the radio ambient.
There are parts of the spectrum set aside for radio astronomy. But we observe all over the place and really have to observe all over the place. So we've been lucky for years by being in the middle of the desert in New Mexico and on a mountain in Atacama. But those days are changing a little bit, which is why we're doing this. The one challenge I didn't mention was Starlink also has their direct-to-cell service. I don't know if you've heard of that, but they're offering a link on your cell phone.
Yes, I read that. Yeah.
So that's not new, except that those satellites were at mid or high orbit, and the latency was just right so that you could hardly talk, right? But now with their low orbit satellites, the latency is negligible, and it's quite feasible to do that. But at the lower frequency, the way it works out, they can't really avoid having a direct interaction on our beam width. So we've started a program. The lucky thing is it's a voice signal, so it's relatively narrow. So we can put notch filters in to block those out. You want that notch filter right up next to antenna before amplification, so that we're building superconducting based notch filters, which is not terribly hard to do with a single fixed notch. But as other companies come online, like Kuiper and other countries are going to be building these, you're going to want to be able to tune that a little bit. You don't want to have to open up your cryostat and take out one filter and put another one in. Now, tunable superconducting notch filter is a very difficult task, so that's another challenge ahead of us. But it's just part of the world we live in. That's going to be the future. It's a crowded, dynamic spectrum in the future. That's just what we're going to deal with. I think you deal with that already here as well, don't you? Yeah.
Thank you.
What frequencies are the Starlink working with this beam changing system?
Oh.
I don't remember very well.
Yeah, there's one at 2 or so, and I forget the other higher frequencies. I may go have one up at S-band and X-band, maybe C-band. I don't recall the exact frequencies. Yeah.
And have you talked about with them, or maybe heard of, about this ground station that Starlink is starting to put in 115 gigahertz or so?
Okay.
You've been working with that as well, or you have
These are
any issue?
uplinks. Yeah.
Both.
Yes.
Uplinks and downlinks.
Yes, as a matter of fact, we did. We got some of those ground stations from them, and we put them near Socorro, near where the VLA is. And so we cooperatively turned those on while monitoring those frequencies. And the bottom line is there wasn't a problem.
Okay.
I don't know whether that was because of line of sight issues or their beam is just good. But the uplinks don't seem to be a problem within tens of kilometers away from the site. Now, when you have ngVLA, you saw those antennas go all the way into eastern Arizona, western Texas, down into Mexico, and even up to Colorado. You can't guarantee that a Starlink station isn't going to be right there, 100 meters away. So that's just something we have to deal with. In interferometry mode, it does wash out a little bit. That interference will,
It's local in one single
right,
antenna.
and that will kind of zero out as you do all your phase work. But these are all things that we will discover in the next 20 years or so.
What are other key objectives of ngRADAR? Is the moon the first, and then you can see more?
Moon and planets.
planets?
These big planetary and asteroids. There's other national defense applications, which I don't know much about, but yeah. Yeah, it'll be a space radar, fully functional.
And what the frequency is that radar? What is that part?
11.9 gigahertz.
Okay.
So that's a trade-off. It would be great to take that up to Ka band because you'd get a lot of gain on a 100-meter dish at Ka frequencies. It's a balance between power. So yes, you would get more gain, but a little less power there. And you also get better resolution. And the other factor is what kind of transmitters are available. The plan is to have an array of mimic solid state transmitters that are power combined. And at about 12 gigahertz, those are available and relatively inexpensive. So it's a trade-off between cost, performance, and 11.9 gigs is where that wound up. Yeah, odd frequency, but it's been interesting. Our test had to avoid the International Space Station.
Yeah, so that was I was going to ask about.
Right, and so at first we couldn't really transmit as long as they were on our side of the Earth, which was very restricting. But NASA has been very good working with us and giving us permission. As long as the angles are okay. We can transmit. But that's another example of a crowded spectrum. The other important mission about the radar is what they call the cislunar space, which is that space between the Earth and the Moon. And I guess as Artemis shows, there's going to be a lot more traffic going back and forth. And it would be able to track a spacecraft all the way out to the Moon. The other thing I didn't know is that the Moon also has a space junk problem, because of all the landers and everything there. I mean, it's not as bad as the Earth, but there are unmapped residue of spacecraft there. Mm-hmm. And as we go there, you're going to want to map that. And it's possible that the radar could help map the cislunar space trash environment.
The moon doesn't have the same drag as we have with the atmosphere here, so I guess.
That's it. I hadn't thought about it. Yeah, they'll stay there forever.
They
won't
stay
they?
there.
Yeah, that's true.
Right.
Like in science fictions.
Yeah, that's a good point. Didn't think about that. Yes.
Go ahead.
The next generation VLA bands are going to be completely different than the current ones. I don't know if I saw it.
Yeah, it'll be wider. It will cover. It won't be completely different. Let's see. The current goes to 50. Is it 50 megs to 50 gigs? Where is it? Oh, where is? I should know that by heart, but I don't. 72 to 50 is a very large array, and so we'll go 1.2 to 116.
The dishes are going to be completely replaced. The current ones too.
Right. Yeah, I remember those current ones are 46 years old now.
Yeah.
So one of the operational challenges we have is how do you bring up ngVLA and bring down VLA? If money were no object, you would leave VLA up and build ngVLA and then one day just... But the same engineers operating VLA are going to be building ngVLA. So that, we're hoping for a very graceful transition between the two. And that's the plan. Do you have a question?
No, it's about the next generation VLA. This spiral geometrical form
Uh-huh.
is based on maximize what?
Let's see. I thought I had down at the VLA section, I think I had it. These?
Yes.
Right, all right, so I'm an engineer, not an astronomer.
Okay.
Here's what the astronomers tell me. You could spend 20 years moving these around for optimization, and it depends on what you're trying to optimize on. Our very good astronomers and planners at NRAO have proposed this, and so I'm going to assume that it meets,
And you
it's
got-
optimized over
Okay,
some
you have
set
the
of,
north and south,
Yes.
and also the east and west, and then the rotation of the year, but the
Yes.
Earth, but
yes.
it's very interesting. And do you have the for sure the places where
No.
okay, so it's a draft.
Right, although it's interesting, I do have some insight into that. These days with GIS databases, you can go a long way to seeing what a potential site is like. How close is it to public utilities, power? Is it on public land or is it on private land?
Okay.
So you can go a long way to eliminating things that would never work out and putting it down in places that at least have a good probability of working out. Yeah, yeah. And the other thing is maintenance. You know, maintaining the VLA now means you must keep people in this area.
Yes.
What? How do you deal with that, right? So it's, which is why the modular receivers we're building, and you know, the single enclosed cryostat, will help with that. The design of the antenna, you may have noticed.
Need to buy good helicopters for the.
So I suggested autonomous vehicles just drive out there. But you see, you can you can drop the down to the subreflector, and there's no climbing involved. You can change that off there. So that's the plan. That's the plan.
Is the open sky or non-open sky policy already discussed? Share with Mexico or?
Oh yeah, sure. Our partners will have
Yeah, but
observed.
what is
For the rest of the.
for the rest of the world? It's like the VLA or it will
I think
change?
I think the intent is for it to be an open sky. I think that's the intent. Yes. Okay.
Okay, we thank you.
Thank you.
Bert again.
Thank you. Saved my life.